This is the video solution for homework 11 question 2, and we are given 3 functions, and the question asks us to find if the function could be representing an autocorrelation function or a spectral density function by replacing this V into tau or omega. So if R tau is an autocorrelation function of a real WSS stochastic process, so it must satisfy the following properties. The first one is R tau must be an even function, and the second one is R tau's biggest value is at 0 when it gets 0, so R tau is smaller than R0, smaller or equal to R0. And third, the Fourier transform of R tau must be non-negative, and when it goes on a spectral density function, so it only must satisfy only one properties, that is it must be a non-negative function. So let's begin with the first function, a f v equals to e to the power of. So let's check the first 3 properties of an autocorrelation function. R tau is even. F minus v equals to e to the power of absolute value of minus v, which equals to fv. So it's an even function. And the second one, to check whether this is smaller or equal to e to the power of 0, which is equals to 1. And it's obvious is this condition is satisfied. And the third condition, by checking the transform pairs, we can get its Fourier transform is 2 alpha divided by the sum of alpha to the alpha power plus omega's power, and this is non-negative, this is non-negative, this is non-negative. It's obvious and non-negative function. So the equation A, the function A could be representing an autocorrelation function of a real WSS stochastic process. And the second part, to check whether it could represent a spectral density. So it's obvious a non-negative function, so it could be a spectral density function too. You go on, the second function fv equals to sine v's power divided by v's power. The first one, f minus v equals to obvious and even function. And by deriving these two parts, we can get this limited is 1, this value is 1, so it's obvious gets its biggest value at 0 point. In the third part, its Fourier transform is looking like this. Which is obvious and a non-negative function, so it could be representing an autocorrelation function, and it's obvious its value is forever greater than 0, so it could be a spectral density function too. And come to the third equation. It's look like this. Alpha. And its Fourier transform is this is not a non-negative function, so it couldn't be an autocorrelation function, and it's with a non-negative function, so it could be a power spectrum function.